I'm going to try and explain about moles and how to do the moles work within GCSE. What I'm about to do normally would span 2 years. We would do a bit in year 10 and we do the harder bits in year 11. And to be fair, the harder bits aren't much harder. So I'm going to do all of it in one go. I hope you can keep up, but if you just need the year 10, then stop the video. And I just think it makes sense, if I'm going to record it, to record all three aspects of the types of calculations you get. So this topic, moles, is a topic that deals with quantities of chemicals. And the quantities of chemicals are like, if you want to order some chemicals, are you going to ask for 10 molecules, or are you going to ask for 200 billion atoms, or would it make more sense to ask for a gram of salt, or 10 litres of oxygen gas? And what makes sense is to ask for masses. So you can weigh chemicals. If you weigh them, that will be dealing with masses and weights. Or you can measure, if you've got a gas, you can measure the volume. Or the third aspect is about solutions. And as I say, we tend to deal with these later in year 11, but with solutions, where you've got a solute dissolved in a solvent, then you have to know about concentrations. And to deal with solutions, we measure their concentrations. To deal with gases, measure their volumes. To deal with normal chemicals we can weigh, then we weigh them. The proper way to say that is we will take the mass of them. And that's what this topic is about. It's about how do we get the ideas of moles over into your heads? Because the majority of the topic is about doing calculations. It's a mathematical calculations topic. What I'm going to do today is to go through all the ideas. And the ideas give you the logic on top of which you can do all the calculations. So don't just skip over the ideas. Get the ideas sorted, and then you'll find the topic easier. So let's start. If we're dealing with chemicals, let's start with the smallest of chemicals. 1 minute, I'm just going to close the door while the rush happens between lessons. As children swap, then there'll be a noise in a minute. So I'll close the door so that we can not be disturbed. But I want to start with having a discussion about the lightest of all atoms. And if you look on the periodic table, hydrogen is the lightest, and you've got all the others. Everything else is heavier. And if we look at probably the biggest of our atoms, lawrencium, on the periodic table I'm looking at up there, then lawrencium is typically 250 times more heavy than hydrogen. Hydrogen is the lightest, and lawrencium is the heaviest on that periodic table. I mean, there are some new elements that are heavier, but they're not on that periodic table. And it doesn't matter. What I'm trying to say to you is, you've got all these atoms of all different elements, and all of them weigh different amounts. And as they weigh different amounts, we have to get to grips with how and what causes their weight. So I've got the lightest atom, as I say here, hydrogen. Hydrogen is a proton in the nucleus surrounded by an electron. The electron whizzing around the outside. Now, previous lessons, you should have learned from me that electrons have a negligible mass. That means their mass is so small we don't have to factor their mass into our discussions, etc. In fact, you need about 1,836 of these electrons to make the weight of one proton. That's why it's negligible. It's tiny. The weight of a proton and the weight of a neutron are the same, and they're not negligible. They are what give atoms their masses. So when we're talking about the weight of one of these hydrogen atoms, then we can't just get it and put it on a balance, because the weight of atoms individually is so small as a function of the atoms being so very, very, very small. If I was to ask you a common sense question like, I've got a sheet of paper, how much does it weigh? And you put that on a balance, and it doesn't register on the balance because it's too light. Then one way around that might be, why don't you take 1,000 sheets and weigh them on a balance? And having weighed 1,000 sheets, then the weight of one of them is 1,000th of the weight that you register when you've got 1,000 sheets on the balance. So, using that idea and extending that to the hydrogen atom is so very, very tiny, we cannot weigh it. So how many of them? Let's take a huge amount. Let's take loads and take a huge amount and see how many of those we need to register a mass of 1 gram. Now 1 gram isn't huge. 1 gram is tiny. Well, it's not so tiny. That pen weighs about 10 grams. So it's about the 10th the weight of a pen that you're writing with. It's not very, very small, but it's not huge. So if the smallest atom, hydrogen, and its weight is due to the proton that's in every nucleus, we need how many of them to give us a mass of 1 gram? Well, we're going to need a large number. Hopefully my next slide will take you through this number. So we need, in fact, that many. 602,000 zeros. We need a large number. Now, what is that large number? That large number is 6.02 times 10 to the 23. So that's roughly 6 and 23 zeros. Now that clearly is a large number, but how large? I think for young minds it's unimaginably large. People cannot imagine it. It's that large. I know you say large, you think, oh, large. But if I try and quantify it, how many grains of sand on Earth? I would say about that much. It's that large a number. Now, I do another calculation in class sometimes. I say, let's assume everybody's a millionaire. If everybody's got £1 million, how many pennies? If you had pennies and everybody was a millionaire, how many pennies on Earth? Not that number. So all the wealth of the Earth added together in pennies is not 1 mole. Sorry, not 1 mole. Sorry, I don't use the word mole yet. But it's not that large number. What I'm trying to say to you is that large number of atoms of hydrogen giving 1 gram is such a large number that we need to give it a name. And the name we give it is a mole. We call it a mole. This huge number is what we call a mole. And the basis of this topic is based on that number. And that number is also called the Avogadro number. And then sometimes you need to know it's called the Avogadro number. But I'm going to call it a mole. Avogadro's number is a mole, and that mole, Avogadro number, is phenomenally huge because atoms are so very, very, very small. You need a mole of hydrogen atoms, that huge number of atoms, and then that's 1 gram. So, if we had a mole of Lawrencium atoms, they're 250 times bigger. A mole of Lawrencium would weigh 250 grams. And that's the weight of a cup of coffee. So, the lightest of our atoms, 1 gram. The heaviest of our atoms, 250 grams. If you take a mole of atoms, this idea of taking a mole of atoms puts atoms onto a manageable weighing scale. The lightest ones being 1 gram, which you can weigh, the heaviest ones being 250 grams, which you can weigh. The concept of a mole being 6 and 23 zeros ties in nicely if you want to weigh things. Now, if instead of 23 zeros you had 24 zeros, then a mole of Lawrencium would be 2.5 kilograms, which is a bit too heavy. Or if you had 1 zero less, you had just 22 zeros. Then the 22 zeros would make weighing a mole of hydrogen really hard, because it would be 1/10 of a gram, and 1/10 of a gram, you're going to have really expensive balances in order to weigh 1/10ths and 100ths and 1,000ths of a gram. So it's just the right quantity. A mole has been chosen as the big number that we're going to look at taking that quantity of atoms, of hydrogen, of lithium, of sodium, of magnesium, of oxygen, of nitrogen, of all the elements. We're going to take a mole of them, atoms, and we're going to work with what they weigh. And if we know what the atoms of elements weigh, then we should be able to quantify and work out the weights of compounds, because compounds are made of elements. And let's get into that then. Let's get into this topic. I don't know if you can read. I'm in this lab. It's a bright day, which makes the board, the projector, not project so clearly. But I've got a penny there, and what I'm saying is that if we have a mole of 1p pieces like those, then how much money would we have? A mole of 1p pieces would be a millionth the wealth on our earth. Let me say that again. If you had 1,000,000 earths, all the wealth on 1,000,000 of our such earths would equal 1 mole of 1p pieces in terms of money. I hope that makes you see just how phenomenally large that number is. And that's why I say it's unimaginably large. And you don't have to imagine it. I just want you to know that whatever mental picture you get of what a mole is, an actual mole is much, much larger. So I want you to treat the word mole, representing that large number, in the same way that we have the word dozen to represent the number 12, or the word score to represent the number 20, or the word gross, which represents the number 144. Now, dozens or scores or gross are using words to represent numbers. And that's what we're doing here with the moles topic. 1 mole represents the Avogadro number. The Avogadro number is 6 and 23 zeros. The Avogadro number is the number of hydrogen atoms that would give you 1 gram of weight in terms of hydrogen atoms. And that's where the fundamental understanding starts for this topic. But of course, other things like lithium are not made of just 1 proton. So mole of protons is 1 gram. That's the hydrogen argument. But what if you got a mole of something like, that's an atom of lithium. Now lithium's got 3 protons and 4 neutrons. Remember, protons and neutrons weigh the same amount. So that atom there on the board is 7 times heavier than hydrogen atoms. And so a mole of those would weigh 7 grams. Now if you look on a periodic table, you see this? Lithium symbol, 7 and 3. 7 is what we call the mass number, and 3 is the atomic number. The atomic number tells you how many protons you've got, and the number of protons is 3. The top number, the mass number, tells you the number of protons and neutrons, and that number of protons and neutrons is 7. And that is 7 times as heavy as a hydrogen atom. So really we can focus on the top number. The top number is the total number of protons and neutrons added together. If we focus on the big number, then we can get a sense of any atom on the periodic table, what a mole of it will weigh, because we look at that big number. So a mole of lithium atoms would weigh 7 grams. Let's look at other atoms. Sodium atoms. The top number is 23. So a mole, 1 mole of sodium atoms would weigh 23 grams. A mole of oxygen atoms, top number is 16, would weigh 16 grams. A mole of carbon atoms, the mass number is 12, would weigh 12 grams. So, one other thing, I know it might seem a bit random, but it's not, because we need it in a definition. How about a fraction? How about if you had a 12th? 1/12 a mole of carbon atoms would weigh not 12 grams. A mole of carbon weighs 12 grams, but a 12th of a mole of carbon atoms will therefore weigh 1 gram. This 1/12, the mass of a carbon-12 atom, is used as the reference. So we're going to call, or we're going to build up to a definition of relative atomic mass. And that relative atomic mass, whenever we have the term relative, then that term relative, we have to stipulate what we're comparing against. The word relative compares against something. We have to have an industry standard. And the industry standard for moles is that one. It's like, take 1/12 a mole of carbon-12 atoms, which weigh 1 gram. That is what we compare against. So 1/12 a mole of carbon-12 atoms weigh 1 gram, the same as a mole of hydrogen. And everything is then put on a scale. 1 mole weighs the lightest hydrogen atom will weigh 1 gram. The heaviest Lawrencium atoms weigh 250 grams-ish. And everything else in between is manageable. This quantity of a mole, being that precise number, gives you manageable quantities in terms of weighing and volumes and concentrations. So that's why we use it. Your teachers will have told you to learn the definition for relative atomic mass, and some of my pupils who don't understand it so well, they just blatantly parrot fashion learn it. And I want you to just learn it parrot fashion. Right? Try and understand it, but if you don't, then learn it parrot fashion. Definition of relative atomic mass. Now the symbol, capital A subscript R, is the symbol we use for relative atomic mass. And the definition is, it's the mass of an average atom. So it's a mass of an average atom of an element relative to a 12th the mass of a carbon-12 atom. So we're going to compare everything to 1/12 the mass of a carbon-12 atom, as I explained. Learn that, that's in the bracket, relative atomic mass definition. They ask it, and you need to say it like that. Now, there are other ways of saying it. There are about 3 acceptable ways of saying it. That's just my preferred way, where I talk about the average mass of an atom. But you could talk about the mass of a mole of atoms, but then you've got to compare against a mole of carbon-12 atoms. Your teachers may find some other way of saying it, so you just have to go with whatever you're taught by whichever teacher. But that gives you the marks in a GCSE, and that's one that I get my boys and my pupils to learn. So those are what we find on a periodic table. So if I get to a periodic table, which I haven't got a periodic table on me here, but any periodic table, specifically the GCSE periodic tables, they tend to have the 2 numbers. The top number, the bigger number, is this relative atomic mass number. And the bottom number is the number of protons. So on a periodic table, these are the numbers we're going to find. And of course, these are the numbers we need in our topic of moles, because these numbers to us represent masses of atoms of any element that's on the periodic table. Now, I want to get into how we get to these relative atomic masses. Now, this is a higher level argument, and this higher level argument is going to involve things called isotopes. And the most famous argument with isotopes is the argument to do with chlorine. Now, chlorine atoms, as you may have seen in a previous video, chlorine atoms, there are 2 types of chlorine atoms. Now, for atoms to be chlorine, they're going to be chlorine if they've got 17 protons. So 17 protons makes that atom chlorine. 17 protons makes that atom chlorine. So that atom of chlorine has got 18 neutrons. And that atom of chlorine's got 20 neutrons. So those atoms are heavier. These atoms are lighter because of different numbers of neutrons within them. The neutrons weigh, and therefore the isotope with less, the isotopes with less neutrons are the lighter ones, and the isotopes with more neutrons are the heavier isotopes. So if we were to weigh a mole of these, they would weigh 35 grams. If you were to weigh a mole of those, they would weigh 37 grams. But chlorine isn't one or the other. Chlorine, wherever you find it on our Earth, chlorine is mixed. So you have to know what proportions each of these is. And I've written it, I don't know if you can see, but 25% of all chlorine is the heavier type of chlorine, and 75% is the lighter type of chlorine. And so for every 3 chlorine atoms that weigh less 35 protons and neutrons, you've got 1 atom of chlorine 37 with 37 protons and neutrons. The ratios are 3 to 1, or 75% to 25%. And how do you work out an average? The average is not halfway between 35 and 37. The average is not 36. That would be a direct average. We want a weighted average. Now, weighted averages will give more weight to the atoms that occur most frequently, and they will give less weight to the atoms that occur less frequently. And the word to use is abundance, not frequently. Abundance is to what extent something exists on our Earth. So chlorine 35 is 3 times more abundant than chlorine 37. And the average mass of a chlorine atom must take that into account. And I'm going to work it out now. That's why I'm standing here behind it. I think just to cover up the calculation, but I'm going to show you how to do the calculation. And the calculation is easily done if you know percentages. And I would ask you to convert fractions. If you're given fractions, convert the fraction to a percentage and use percentages. Because what I'm going to do is, I'm going to take 100 chlorine atoms and I'm going to divide by 100 to get the weight of one of them. So how do I take 100? Well, out of every 100, 75 of them are the lighter one, that weighs 35 each, and 25 are the heavier ones that weigh 37 each. Add all of those 100 up and divide by 100. Look, here. 75 times 35. That's the weight of 75 lots of the lighter atoms. Add 25 lots of the heavier 37 atoms. So that is a way of getting the weight of all 100 typical atoms. You divide by 100 to get the weight of one of them. So put that into your calculator, divide by 100, you get the answer 35.5. Now 35.5 is the relative atomic mass value of chlorine. Look on your periodic tables. Chlorine, the top number will be 35.5. Look at the key. The key on the periodic table, the legend. The key will tell you that the top number is relative atomic mass. Learn the definition for relative atomic mass. The mass of an average atom relative to 1/12 the mass of a carbon-12 atom. That number on a periodic table is what we're going to use in this moles topic. So if we want to know the weight of a chlorine atom, we're going to use 35.5. That's the average weight of a chlorine atom, 35.5. And if you look at copper, 63.5. Sadly, those two, chlorine and copper, are left as decimals and everything else is rounded. So magnesium, which has a relative atomic mass of 24.3, look on your periodic tables, it says 24. The decimals have all been rounded. And the annoying thing is, I don't like that inconsistency. Why do you round everything and don't round the chlorine and don't round the copper? It makes no sense. At A level, our A level periodic tables have all of the elements to one decimal place. I like that. That's consistent. But GCSE is strange in that respect. But look, I can't change GCSE. I just want you to deal with it. So get over it, deal with it. Chlorine, 35.5. Copper, 63.5. And everything else has been rounded. Hydrogen is 1, rounded to 1. Sodium rounded to 23. Magnesium rounded to 24. Look at any periodic table that you get. You're going to have to get your mind around the one that is for your syllabus. Look at that one and be able to use these numbers. So, if you know how to get to these numbers, relative atomic masses, then how do we use them? Well, before I go on to the next slide, let me tell you that we have many terms in chemistry that are relative. And this is relative mass. But we could talk about relative volumes, relative density, relative diffusion rates. And each of these relative terms only makes sense if you define what is relative to. And all of moles is relative to 1/12 the mass of a carbon-12. And when you've got things that are relative, they never, ever, 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 ever have any units. So don't put units in. The mass of chlorine is relatively to 1/12 of carbon-12, 35.5 times bigger. It's a factor, 35.5 multiplied by what your relative term is. Don't put grams, but what if you do a mole of atoms? Well, a mole of atoms will weigh 35.5 grams. So the sentences and the way I want you to use language is crucial, and I want you to use it like this. So, a mole of chlorine atoms have a relative atomic mass value of 35.5. That's got no units, no units. But a mole of chlorine atoms will have a mass of 35.5 grams. So a mole of chlorine atoms will weigh 35.5 grams. Let's move on to something other than chlorine. On your periodic tables, find sodium. A mole of sodium atoms. Well, first look up sodium, and the relative atomic mass value on your periodic table will be 23. That 23 is no units. But what about a mole of sodium atoms? They will weigh 23 grams. So the weight is 23 grams, but if you just want the relative atomic mass value, no units. You only use units if you're talking about masses, if you're talking about RAM values or relative atomic mass values, AR values. Never, ever, ever use units. Otherwise, you're going to lose marks. And how about a fraction? Well, what about a fifth? A fifth of a mole of oxygen atoms. Well, find oxygen on your periodic table. Oxygen's got a relative atomic mass value of 16. So your periodic table will tell you it's 16. And that would be 1 mole would weigh 16 grams. But we want a fifth of a mole. So a fifth of a mole of oxygen atoms will weigh 16 divided by 5, which is 3.2 grams. Now, I've made a mistake there. That should be oxygen. I'm talking about oxygen here, and I've put the word chlorine. Typical Ahmed mistake. I'm sorry. I make such mistakes. If you don't like it, then I don't know what to say. I don't deliberately make them. But if you don't like me making such mistakes, perhaps it's better you do not watch these videos. I always, and I believe human beings make mistakes. So, I would just ask you to get over it, or don't get over it, don't watch my videos. Right. So, let me just say those things again in a converse way. A mole of chlorine atoms weigh 35.5 grams. See the word grams? Because it says a mole weigh 35.5 grams. But the AL value is 35.5, no units. A mole of hydrogen weigh 1 gram. But the relative atomic mass value of hydrogen is, on a periodic table, just 1, no units. A mole of carbon weigh 12 grams. But the AR value of carbon is 12, no units. A 12th of a mole of carbon atoms weigh 1 gram. The relative atomic mass value of carbon is 12. So, this is in red here. I don't know if you can see that in red. A mole of any elements, atoms. A mole of any elements, atoms, will weigh the relative atomic mass value that you find on a periodic table in grams. But the relative atomic mass value will be that value with no units. Your teachers will stress this point as well. So, real chemicals are typically not made of just atoms. They're like different atoms together. And so if we want weights of real chemicals, then we just add up the weights of the individual atoms that make them up. So water. Water made of hydrogen and oxygen. If you know the weight of hydrogen, the weight of oxygen, the weight of water is just the weight of the hydrogen, weight of oxygen together. The total weight of water will be the weights of the hydrogen atoms added to the weight of the oxygen atoms. That's the idea. So how do you know how much of each to take? Well, you look at the chemical formula. Remember, in year 9, I did say writing formula is crucial. And you need to be able to write the correct formula in order to do this moles topic. So go back and revise how to write formula again and to write it correctly. And when we can write the formula, then we come up with this concept. The concept of relative molecular mass. MR values, relative molecular mass. Again, it's the same thing. MR is a relative term. Relative term do not have any units. So MR values have no units. But if you were to weigh a mole of them, then they would weigh that much in grams. The same idea that I've been stressing with atoms applies to real chemicals. But with real chemicals, we need formulae. Once we've got the formula of the chemical, then we can work out the weight of a mole of it. So, calculating the MR value, that's what we're trying to do. We add together all the atoms that make up that chemical. So water, 1 mole of water will weigh hydrogen, 1 gram, hydrogen 1 gram, oxygen 16 grams, to tie up with H2O. H2, 2 hydrogen, 1 oxygen, 2 hydrogen, 1 oxygen, H2O, 18 grams. The MR value of water is 18, no units. Now, let's do something a bit more complex. Sodium sulfate. Look at the formula. 2 sodiums, 1 sulfur, 4 oxygens. 1 mole of sodium sulfate will weigh, that's 1 sodium, another sodium, a sulfur, and 4 oxygens in brackets. Add them all up, and you get 142 grams. So a mole of sodium sulfate weighs 142 grams. But the MR value is 142. The MR value, 142, no units. I hope you get the point. I'm going to make it once more probably with oxygen. Oxygen gas. Now, a lot of people use the word 16 with oxygen. Sorry, the number. A lot of people use the number 16 with oxygen gas. Oxygen gas is always O2. It's never ever O. You need 2 of them to fill up the outermost energy levels of electrons. 2 of them together sharing electrons. You need a double covalent bond between the oxygens. If I want to write it on the board, I would go oxygen, double bond oxygen like that. That's why it's O2, and it's a gas. And it's never O. The real chemical of oxygen is never ever O. And if we want to work out for a real chemical how much a mole of it weighs, then you want the real formula, the O2. 1 mole of oxygen atoms, sorry, not oxygen atoms, 1 mole of oxygen gas. Because it's made of those molecules, O2 molecules, 2 atoms in every molecule, then a mole will weigh 16, add 16, each of these is 16 each, 32 grams. A tenth of it, a tenth of a mole of oxygen gas, will clearly weigh a tenth of that, 3.2 grams. Or the MR value of oxygen is 32, no units. Note that out. We can go to the next slide. You have to get your mind around what AR values are, and you add those AR values together to get what the MR values are. It's the MR values we use in the real world because the MR values reflect real chemicals, and in order to work them out, you need to know the formulae of those real chemicals. Right, let's move on. So if we've got a mass, say you're given 2 grams of water, how many moles is that? Well, if you know 1 mole of water weighs 18 grams, and you've got 2 grams, then 2 over 18 is 1/9, a ninth of a mole, 1/9 of a mole. So we need an equation, we need a mathematical equation that will help you deal with that in a in a way that you can rearrange it to get whatever it is you need, etc. And the mathematical equation I want you to learn is that one. Look here, the number of moles is mass over mR. So this is really important. So number of moles is mass over mR. Hope you can see that clearly. N is number of moles, mass of a real chemical, divide by mR value of that real chemical. How are you going to work out the mR value? You're going to add up the atoms that appear in the formula, and that's going to be your mR value. And that's how you work out number of moles. So with water, say you've got 2 grams over 18, the number of moles would be 1/9, and you get your calculator out, do 1 over 9 and kind of work it out, etc. So I want you to mathematically, that's the first of 3 equations. It's the first of 3 types of calculations that you're asked to do. And most of the marks you can get by learning the 3 equations and doing the calculations. As I say, this video is all about understanding, and I want you to understand these things. So, I think I've been going on for 41 minutes. I'm going to stop it there. And then I'm going to carry on, but in a different video, because I don't think people can watch videos that are so long. So let me just stop it there, and I'll carry on the recording in a minute.